lecture was recorded appropriately, if one has checked this. Last lecture. I'm always forgetting to switch on this recording. I remember last year there was a student who was sitting in front and he was always reminding me to switch on. And now nobody is actually reminding me to switch on the recording system. So if something is wrong, tell me. Okay, so what is this? Can you hear me? Now, can you hear me?
Yes.
Okay. So I was just saying that sometimes I'm forgetting to switch on recording system. So please then tell me if something is wrong. Since last year, it was one student who was sitting in the front line, and he was always reminding me to switch on recording. But then now nobody is sitting here, so I may just forget it. Okay, so let us start, and let me see, probably there's some light to have blackboard, as you know. No. I think this is the best what we can do. So today we will discuss interaction of particles with medium. This is an important issue because we are getting information about particles precisely looking how they interact with medium. Let me remind you that, for instance, electron was discovered when the beam of electrons interacted with target. With a screen producing the shining spots. Similarly, nuclei have been discovered by detection of alpha particles scattered on nuclei. And these alpha particles also produced shining spots on the target. So this is the result of interaction of particles with medium. Today we will discuss how particles produce tracks in the medium. So passing through the medium, particles produce ionization, for instance, or emission of light. And then we are detecting the secondary effects of these interactions. So we have an elementary particle producing first some tracks in medium, and then we do something which actually allows us to see these tracks. So sometimes the effects produced by particles still are not visible. But then we are doing them visible. And this is the way we are getting information about elementary particles. So we need to understand how tracks actually depend on properties of the particles. So tracks encode information about elementary particles, their interactions and properties. And so we need to decode what we see in our detectors to get information about elementary particles. The observable effects are proportional to energy loss of particles, or proportional to energy loss on the unit of length. It's proportional to it's dE over dx. And in fact, all the effects we are observing eventually comes from the energy loss of the particle. If particle propagates without energy loss, that we will not see any effect. The bigger the energy loss, the clearly we see the tracks of the particles. We usually measure this quantity in the units MeV over centimeter. Again, energy loss on the unit of length. Suppose we have electron or proton which enter the medium. So which kind of the effects we are expecting to have? Tell me, who knows, what are the effects they are producing in the medium? Suppose you have a detector and electron enters the detector. So which kind of effects you are expecting to have in the detector?
Radiation.
Yes. Okay. So it will be radiation. It will be radiation energy loss. So why particles should radiate something, by the way? So you have medium which consists of neutral atoms. Why the particles should radiate something? Well, you will see it starts to radiate when wavelengths of the particle becomes smaller than the size of the atom. As we discussed before, in this way, the particle fills in the inner structure of the atom, which means that it fills electrons and nuclei, which are charged. Of course, if you have very low energies, then the particle sees the atom as a neutral object, and there is no strong effect of scattering. Still, there are some small effects, but mostly radiation occurs when the Broglie wave of the particle is small enough. So what else particle can produce? It can produce ionization of atoms, right? So the particle can hit electrons in the atom and knock out one or even several electrons from the atom. And of course, it loses the energy doing this. So this is ionization of atoms and ionization energy loss. What else? Particles like protons, neutrons, which are strongly interacting particles because they are composing the nuclei, they can suffer from nuclear interactions. And produce so-called hadron cascades, produce secondary strongly interacting particles. There is another very important effect which actually doesn't take much energy from the particle, and this is Cherenkov radiation. This is extremely important effect which allows to measure properties of the particles without actually taking much energy from the particle. So this is very important, of course. So we will discuss in this lecture and maybe in the next one these three processes, because you need really to understand this physics of these processes to understand how further development of particle physics occur and how particles have been detected. So the first we will discuss radiation energy loss. So what happens if your probe particle L approaches another charged particle, or approaches atom, which is composed of charged particles? It interacts with atom and emits photon. So this is, if you want, graphical or schematical picture of the process. These charged particles create electric field, and so our probe particle scatters in this electric field. It changes trajectory because of action of electric force, so it accelerates or decelerates, and therefore it can emit radiation. I think you also studied this from quantum mechanics or even early classical mechanics, classical electrodynamics cases. So here we also put gamma. So this is the diagram precisely. So what happens again? Charged particle interacts with charged particles in the atom. So this is atom. So which means that it interacts with electrons and nuclei and emits gamma. The photon can be emitted both, as we are saying, in final state, as it is here, or in initial case. So there's another diagram, let's say, when the gamma is emitted here, and here we have scattering on atom. The energy loss, dE over dx, in this process is proportional to the energy of this particle. It's proportional to dL. And this is total energy loss when you do integration over the energies of photons. So you have photons emitted with different energies, right? And so when you do integration over all possible momenta and energies of photon, which appears here, the only unit of the dimension of energy is the energy of initial particle. And therefore, nothing you can write but this. The change of the energy and the unit of time and the unit of distance is proportional to the energy of the particle. By the way, let me write still a question for these processes. So we have, for instance, lepton, which interacts with atom, which has Z and A. And in the final state, we have again the same particle, L, plus the atom ZA, and plus gamma. So this is the reaction which we are studying. Okay, so let me repeat the argument. The energy loss, I should probably put here L. And L can be electron, muon, proton, charged particle, any charged particle, probe particle. Just on the dimensional ground, you can write that this change of the energy, it should be proportional to the energy of the particle itself. Now, to have correct dimension of all this expression, we should write that dE over dx equals energy over some length, which we call radiation length. This is parameter which includes everything in this formula. So all the rest should have dimension of the distance length, and we call this distance radiation length. So radiation length doesn't depend on energy. On energy of our particle L. So all the energy dependence is here. However, we will see this explicitly. We will have explicit expression for radiation length. And in this way, we will convince ourselves that indeed L doesn't depend on energy. Now, if L doesn't depend on energy, then the equation can be easily integrated. By the way, it should be minus sign, right? The energy decreases, and therefore we need to put here minus sign. This is important. So it's minus sign. The energy decreases. The integration is trivial, and it gives for us that energy of particle equals initial energy multiplied by exponent minus x, and here is Li. So what you are doing here, you have here dE, you divide this over E, and so you will have here dE over E, and here you will have dx over Lr, okay? And then doing integration, that gives you logarithm, and here you will get on the right-hand side x over Lr. So you have logarithm, and then you get this expression for the energy. And this is some initial energy. At x equals 0. So this is energy when x equals 0. Clear? I think no need to, you can do this. But tell me if it's not clear. According to this formula, radiation length is the length over which the energy decreases by 2.7. So over Lr, energy decreases by 2.7. So energy decreases by 1 over 2.7 initial energy. So this is the meaning of radiation length. This is kind of, so to say, phenomenological description. We just introduce this dependence, introduce radiation length, but eventually we can derive expression for radiation length. Questions?
One question, Professor. Why did we say that the energy loss is proportional to the initial energy of the particle?
Yeah, this is the energy of particle, because what's going on? It interacts. This is precisely the energy of particle. So what happens is that our particle L, in fact, interacts not just with single atom, but with many, right? So there are many atoms on the way. And we take some thin layer, dx, and wondering what is the energy loss of the particle in this layer, dx. So our energy L is the energy of particle when it enters this layer. Okay? So, but eventually you need to integrate over x, everything. And here, so suppose now we have layer. Then our EL0, this is something which enters, this is the energy when particle enters all your detector. And then it loses the energy exponentially in this way. When we derive this differential equation, again, the logic is that we are taking small layer, and then this is energy when particle enters, and there's small change of energy dEL, and it is given by this expression. So you can write that dEL in small layer is given by energy L. This is the energy of particle which enters over LR, and this is dx. Okay? And then you do integration and you get this expression. Sorry. More questions? Okay, clear? So let me now explain how LR can be computed. So what we will discuss now, computation of radiation length. dE over dx actually can be written as minus average energy of photon which is produced in the interaction multiplied by sigma, cross-section of the process, and multiplied by the number density of atoms. So what is this sigma times NA? This is nothing but probability of interaction. In unit of length. Remember we had last lecture the formula for the probability when particle pass through the detector of the size L. And now L is unit, and therefore that gives us the probability of interaction in the unit of the length, and or number of collisions if you want. And this is the energy loss average in each collision. So to say, number of collisions multiplied by the energy loss in each collision. Now, this average E gamma can be written as Y and the energy of particle. I will omit this subscript L. And therefore the energy loss is given, can be written as minus E multiplied by Y multiplied by sigma multiplied by NA. So this is dE over dx. And you see what is here is explicit expression for 1 over L radiation length. So inverse of radiation length is given by cross-section, number density of atoms, and fraction of the energy loss by radiation of gamma. Okay? Let me write final formula. Of course, I have no time, and actually, you are not at the level to derive this formula. But it has very simple interpretation. And what I will do, I will write the formula, which is exact formula, and explain the meaning of various terms in this formula. So explicit computations give us that dE over dx equals 4 alpha cube, and alpha is E squared over 4 pi. This is fine structure coupling constant. Multiplied by 1 over the mass of L particles squared. Multiplied by some factor which depends on Z charge of the nuclei. So it can be written like F Z squared, it has two terms, plus F prime Z. And then we multiply this by NA and multiply by the energy of particle L. Okay? So all this is 1 over L radiation, right? So all the factors apart from E is radiation length, inverse radiation length. So there are 3 factors, and let me explain the meaning of these factors and why they appear. So Z is charge of nuclei, and Z is also the number of electrons. So we are just considering the neutral atoms. Again, this is mass of the particle. And these are some coefficients, but you need to really do computations to find this. For instance, this F it contains the factor like logarithm of 1A3 over Z1 over the third. So this doesn't depend on Z. And this is so-called screening factor. So if you have particle, you have nuclei with many nucleons, or with protons inside, and they somehow shield the effect of scattering. And therefore, so when you increase Z, the net factor decreases. But let me explain the rest. So there are some factors, but what for me is enough to actually discuss this general form. Also this. So alpha cube is clear because we have the process of the following type. Let me remind again. We have electromagnetic coupling here, We have electromagnetic coupling here and here. And so this is third order of the process in the electromagnetic coupling constant. And therefore, the amplitude of this process will be proportional to EQ, right? Because we have 3 points of interactions, these photons. And each of these points gives this factor, electric charge. Now, the probability is amplitude squared, and therefore the probability of the process will be proportional to E to the 6th power. And this is precisely in this alpha cube. Now, the second factor is 1 over the mass of the particle squared, which is very important particle. You will understand many things if you remember this dependence. By the way, I have forgotten to say that this formula, let me write it here, is actually valid not everywhere, but it is valid when momentum transfer Q, momentum transfer here, so this is Q, is momentum of this gamma which we exchange. If this is in the range from keV to 0.1 GeV, or in the distance units, that would correspond to 1 over Q from 10 to the minus 13 to 10 to the minus 8 centimeters. So what are these numbers? 10 to the minus 8 is the size of the atom. 10 to the minus 13 is the size of the nuclei. So this means that the formula is valid when the Broglie wave, and it is proportional, it is just determined by 1 over Q, say 2 pi over Q. When the Broglie wave is smaller than the size of the atom, this is atom, it's something like this, but is bigger or much bigger than the size of the nuclei. Well, actually, this is important range, and many experiments are precisely satisfying this condition. Now, let me come back to this 1 over mL dependence. Again, I will present kind of physical derivation, just to give you an idea. And let's try to use classical interpretation first. So when we have charged particle and another one is moving in the electric field of this particle, it feels the force which is given by E squared over the radius squared. And R is the distance between a given particle and scatter. So when particle feels the force, it accelerates. And again, this is classical expression. The acceleration is given by force over the mass of this particle. And this will be E squared R squared on the mass of the particle. Actually, what is important here is that acceleration is inversely proportional to the mass of the particle. And you probably know this from classical electrodynamics. The lighter the particle, the lighter the particle, the better it accelerates in a given field. It's easy to bend the trajectory. And heavy particles have strong, bigger inertia. You just pass through, and therefore emits less. Light particles get bigger acceleration, and radiation is proportional to acceleration or deceleration. So this is classical analogy, but when we go to quantum analogy. Usually you are using squares, like when you have amplitude, you square amplitude. And therefore, radiation is proportional to, say, a squared, and that will be 1 over ml squared. So this is the origin of this dependence, 1 over L squared. The lighter the particle, the better it emits the light, the better it emits radiation. You can feel this again intuitively. Heavy particle in the same field will, just due to big inertia, will pass through without strong deviation. The acceleration will be smaller. This you can see also from this form, right? So acceleration will be smaller, and therefore emission will be smaller. So bottom line is, the lighter the particle, the stronger radiation. Question? So now let me discuss the third factor, which depends on Z. Can one guess where this comes from? Why we have two terms, one is proportional to Z squared and another to Z? Any idea? So we have this factor which is proportional to Z squared and Z. There is a sum. Of course, if Z is big, then this dominates, and essentially we'll have Z squared. But we have these two terms. Again, my question is, any idea why these two terms appear and what they are related to? So sometimes you see expression that this is proportional to Z plus 1 when F and F prime are close to each other. Explaining this dependence, I will introduce a very important concept of coherence. So let me spend some time explaining coherence. What is this? Again, this is very general phenomena which we will meet many times in our course. So please, it's not only important for this explanation, but we will use these in many other circumstances. So let us consider the system of scatterers within some volume of the size d. So that the distance between scatterers, of course, smaller than this d. Suppose we have wave, radiation, which scatters on this body, and then we have detector at some distance, say that's x, and what we detect here, or look for here, the secondary waves emitted from different scatterers. So we have the wave, it scatters on different scatterers in this volume, produce the secondary waves, and then these secondary waves in particular arrive at our detector. I'm talking about waves, but remember that we are in quantum theory, and therefore so any particle can be described by wave. So it's not only for light, but it's also for electrons, for protons, for everyone. Because eventually we are having the wave nature of our particles. And what is important here is really wave nature of particle and scattering of waves of the particles on some scatterers. So how we will write the probability of scattering? Probability of scattering is given sum of the waves which arrive at our detector moduli square. So that's sum over all the scatterers, and I write here A I. And this is amplitude of scattering on individual scatter I, and this is the amplitude which already arrives here. So I can write this amplitude as moduli of amplitude multiplied by phase factor. This is amplitude is complex parameter, and then I multiply this by the phase. And the phase, in our case, is given by P, momentum, multiplied by XA. I'm considering all the scatterers of the same type, and therefore the amplitudes are the same moduli. But the phases are different because different scatterers are sitting in different places, and therefore distance to our detector is different. So if it's I here, scatter, then this is xi. This is the distance from individual scatterer to the detector. The phases are different. Now, I can continue this in the following way. The probability is given by the sum moduli square plus 2, let me write formula and then I will comment on this, sum over A and J and that will be cosine 5A minus 5J. So for time being, I still keep these indices I. Then eventually I will use the same amplitude for everyone. So you see here we have the sum of different amplitudes. So it's A1 plus A2 plus A3, etc. So I will compute moduli square, and when we open this square of the sum, what we will have square of individual terms. And this gives me this one. And these are cross terms, right? So when I have here, for instance, A1 conjugate, A2, etc., cross terms. And these cross terms, when I express this in terms of moduli, they will contain these phase factors. And so this cosine comes from the product of these phase factors. Do I need to derive this, or it's clear for you? Let me ask. I can do this. So just square to have the square of this, I'm getting this expression. So this is P. Do I need to derive this? Well, let me do the following. You kind of try to derive. This is homework, one of the homeworks to show that this is. Well, nothing difficult here, so I can even give you some hint, because the probability is given by, say, the sum again, I, moduli, phi I, right? Moduli square, and that can be written as sum I this will be plus F multiplied by sum J, Aj minus I F J. So this is conjugate. So I have a moduli square. So first is conjugate of this multiplied by this, and I have, when I square, I have two sums, products of two sums. Okay. Now, when I open these sums, then for the terms when I here and J coincides with I, if I have terms of this type, then the phases disappear, and I will have this first term. Then cross terms will contain the phases, but I have the following terms. I can take term 1 here and term 2 here, or I can take term 2 product and term 1 here. And in this way I will have the exponents with opposite sign in the exponent, and that will give me cosine. Okay? So again, please try that. This is a trivial thing, so just using this and writing in this way, you will get finally this formula. There are two terms in this formula. One is this. When I sum already moduli square of the amplitude, and this is what we call incoherent contribution. So this is incoherent contribution. This is interference. This is interference. This is interference of terms with different phases. Now let us consider two cases. Well, actually, the difference of the phases, let me write here, Fi minus Fj is 2 pi over lambda. This is P, and here is x A minus xj. Right? Now let us consider two cases. The first, when d, the size of the region where scatters are, is much smaller than lambda. If the size of the region is much smaller than lambda, then the difference of the phases is small. So let me denote this by delta phi. So delta phi aj. So again, in this case, difference of the phases is small because the difference of distances is smaller or equal d. Right? So xi and xj, it's just given by the distance between scatterers inside this scattering region. So the difference of xi and, for instance, this xj is smaller than the size of the whole region where scatterers are. So, under these conditions, delta phi ij are much smaller than 1. You see here what we have here is lambda in denominator, and this is again pi. The phase is pi multiplied by x, and I have written pi like 1 over lambda, de Broglie wave. So this is smaller than d, or equal than d, but I divide this by lambda, which is big. And so the phase difference is small. If phase difference is small, then cosine is close to 1. Then cosine delta Fij is approximately 1. And if it is approximately 1, then P will be the sum over I modulo square plus 2, and here is the sum over j and I, and then please show, okay, so I can write it further. So that will be, can be written as the sum over I moduli square and square. So there is no phases anymore here. And I can rewrite this expression as the square of the sum of this moduli. So please show this. What's 3 also? Please show this. That this sum of these two terms, can be written in this way. Oh, sorry, there is no square here. Like that. Sorry. Yeah.
I was saying that there's 2x square.
No, there's no square here, so that's. So which means that if all ij are the same, that this is equal to n number of scatterers multiplied by a, and everything is squared. So where n is the number of scatterers. So, finally, that gives me n squared, the amplitude squared. So which means in such a situation when d is much smaller than the length, the Broglie wave, then the effect is proportional to n squared number of scatters squared. Now let us consider another case. If d is bigger than the lambda, or much bigger, that's opposite case, then the phases are big, so delta f I j are big, so they're bigger than 2 pi, for instance. And now cosine of phase difference is not 1, and it can have different signs depending on different scatters. And when you do this summation, essentially you make an averaging of this cosine over all scatters. And that leads to essentially cancellation, and this term is close to 0, and therefore in this case the probability is given by sum of ai squared, and that is in our case n a squared if all the amplitudes are the same, moduli are the same. So which means that in the case when the de Broglie wave is smaller or much smaller than the size of the scattering region, then the probability is proportional to n, not n squared. This is the coherent case. This is so-called enhancement due to coherence, good coherence. Right? In the coherent case, the result of scattering is proportional to the number of scatterers squared. Here, this proportion is linear to n. And that may be a very big factor, actually, as we will have enhancement of the scattering effect. Well, I can show you this result in a slightly different way. So let me give you another possible derivation. But I again ask you to derive all these formulas, because there's nothing complicated about that if you perform by yourself. So remember we started with P equals this that was our initial expression I, and here our amplitude I squared. So that was our starting point. That can be written as sum I and the amplitudes moduli, again I'm writing with the phase, Fi. And now, if the phase differences much smaller than 1, then this exponent is approximately the same for all scatterers. So what I can write here is to put this phase factor out, phi, and here is the sum over I to n moduli square of amplitude, and if they are the same, then I just write this A moduli. Okay, divided through J. So again, if the difference of the phases for different scatterers is small, then all the phases are approximately the same, right? So that leads to Fi to be the same, F. And this is what I have written here, so that I can put out this phase factor out of the sum, and I will get this expression. So this is common phase, and since it is in moduli square, then I can just drop it down. So that is just moduli, sum over I, and for equal moduli of amplitudes, that will be n a squared. Actually, I can even omit moduli. So that gives me n squared a moduli squared. So this is another derivation, but more or less identical, of the probability in the case of coherence. Questions?
I don't understand the approximation you made, like where you thought the phase is much less than 1.
Say again?
The phase
Phase
is much less than 1, the change.
Phase difference, yeah. So what is not clear?
Could you repeat that?
Okay. Okay, remember we started with system of scatters which is within some, say, sphere of the size d. So this is d at the size. Okay. Now we have detector somewhere here. And let me take here the point x, say, I, and here is the point x, j. And I'm computing the phase difference of waves which are emitted from xi and xj in the point of observer, detector. So this is the detector. So F1, so I equals momentum multiplied by xi. Fj equals momentum multiplied by xj. Okay? Let me delete here. Well, actually, if you want, I can write this in terms of vectors. This is what one should do, actually, to put these vectors and these vectors, but it doesn't change much. Conclusion. So now I'm computing phase difference. Delta F Ij equals Fi minus Fj, and that equals P multiplied by Xi minus Xj. Correct? Okay, good. Now I introduce lambda, the Broglie wave, which is 2 pi over p. And so I can write this as 2 pi over lambda, since I can express p now in terms of lambda, it's 2 pi over lambda. And I get this for this xi minus xj. Now, xi minus xj is smaller or equal d. Is this clear? Because all these scatters are within this volume, and therefore xi minus xj is this distance. Especially if you use vectors, it's clear that if you have vectors here, distance, right? So xi minus xj is this line, which is smaller than d. Okay? Then I can write that delta f ij is smaller than 2 pi lambda multiplied by d. So I substituted xi minus xj by d. And then I consider two cases when d is much smaller than lambda, then I get that delta F is much smaller than 1. Right? So if D is much smaller than lambda, then the phase is much smaller than, say, 2 pi, but you can take it even smaller.
Thank you.
Okay, more questions? So I would strongly advise here to repeat all these things because this coherence is extremely important notion. By the way, people observe this coherence effect, that is enhancement of probabilities by this additional factor n in many circumstances. And only recently, 3 years ago, it was observation of coherent scattering of neutrinos on nuclei. That was, I think, something like 3 years ago for the first time. And this is especially important for neutrinos, which have very weak interactions. And therefore, this enhancement factor will play an extremely important role. I may discuss this later. Okay? So now let's come back to our scattering on atoms. And this is, to some extent, this model of matter, right? So we have atom and electrons. The size of this the atom is Bohr radius, approximately, right? And inside is a nuclei, which is a much smaller radius. Now, when we have scattering with the Broglie wave, which I have indicated in the range 10 to the minus 13 to 10 to the minus 8 centimeters, that would correspond to wavelengths which is smaller or much smaller than the size of the atom, but it is much bigger than the size of the nuclei. What is implication? For electrons, we have a situation when the distance d between electrons, which is Bohr radius, is much bigger than the Broglie wave. This means that the scattering on electrons is incoherent. Right? We have the Broglie wave, which is smaller than an atom, and average distance between electrons is of the order of Bohr radius, and it's much bigger than the Broglie wave. And therefore, scattering, you can think in this way, since this wavelength is much smaller than the distance between electrons, then the scattering on different electrons proceeds independently. So you can consider the scattering of a probability of scattering on each of electrons independently, and then sum up the probability. Therefore, the total result of scattering in this case will be proportional to Z, and Z is the number of electrons in an atom, right? Now, this de Broglie wave is bigger, much bigger than the size of the nuclei. Then for nuclei, and more precisely for protons in nuclei, And they are in the sphere of the radius Rn, the radius of nuclei. Protons are sitting here in a much smaller sphere. For them, d, which is the radius of nuclei, and that will be much smaller than lambda. And this is conditioned to have a coherent scattering. Therefore, scattering on electrons, scattering on protons, inside the nuclei will be coherent. And therefore, the total effect will be proportional to z squared, to the number of protons squared. So this is the origin of two different terms in our expression for energy loss. One term is proportional to z squared, and that is for scattering on protons. And another one is for scattering on electrons. So let me repeat that the formula which we are discussing is valid for the Broglie waves of incoming particles which are much bigger than the size of the nuclei and much smaller than the size of the atom, which is approximately Bohr radius. Now let me ask you the question. Suppose we have lambda which is much bigger, so outside of this range. Suppose we have lambda which is much bigger than the size of the atom. What we will have in this case? Suppose we have a low momentum particle which is coming. Low momentum is that the Broglie wave is much bigger, it's big, and bigger than the size of the atom. So what will be the result of scattering in this case?
The particle will see the atom like units, so it's gonna scatter like two free particles.
So what will be the result for the probability of interaction? So this situation corresponds to atom, and this is nuclei, and the Broglie wave is something like this, much bigger. Again, as we discussed many times, if the size of the wave is much bigger than the size of your structure, it doesn't feel what is inside. And therefore, with this big de Broglie wave, you will feel atom as a whole. And atom is neutral, and therefore it will be scattering going to zero. So, in this case, we go to zero in the first approximation. Now let me ask about opposite situation when lambda is much smaller than the radius of nuclei. What will be in this case? What will be the result of scattering in this case? What will be dependence on Z when lambda is much smaller than the size of the nuclei? What will be dependence on Z? So remember, in this range, we have dependence z squared plus z. So what will be dependence in this case? So that was due to scattering on protons on nuclei. This is scattering on electrons. So this is in our main case. But if I have lambda, which is much smaller than the size of the nuclei, what will be the result? How the scattering and how the probability of scattering will depend on z. You see, it's amazing, right? So we started to discuss these issues from the first lecture when I discussed microscope, how we probe the structure. Even now, today, I discuss it, repeated again the same things. And I'm kind of wondering why you are in trouble to answer this question. At which point, tell me you missed some understanding, because then I try to repeat and tell me if the question is not clear. So in the standard situation when we discussed mostly, we have two contributions. One is from scattering on nuclei, and it is proportional to z squared. Another one is from scattering on electrons, and it is proportional to z. And this is because the first one, scattering on nuclei, is coherent, and therefore the result of scattering is proportional to number of scatterers squared. Scattering on electrons is incoherent, independent on different electrons, and therefore the result of scattering is proportional linearly to number of scatterers, and which is z. Now I'm asking, what will you expect in the case of de Broglie wave much smaller than the radius of nuclei?
Is it 2z?
Sorry, say again?
2 times z?
Right. So in this case, you will have z squared on so no, that's not right. No, so wrong answer. You say what? 2z or what? Again, say again.
2 times the number of scatterers.
2 times z and z. So z for nuclei and z for electrons. Correct. So in contrast to the first case we are discussing, under these conditions, also scattering in nuclei on protons will be incoherent, right? Because our de Broglie wave becomes smaller than the size of the nuclei, and therefore it's smaller than distance between protons inside the nuclei, and therefore scattering on protons will be incoherent. and therefore the result of scattering will be Z. Okay? So correct. So under these conditions, the result is like this, Z plus Z. Good. So let me probably give some number, and you will have exercises I will probably give tomorrow, the first set of the exercises. We discussed the radiation lengths, and radiation lengths, just one example, equals 0.56 centimeters for electrons in lead. So if you take lead and the electron enters, then radiation length is 0.56 centimeters, which means that if you take some material of the size, say 1 centimeter, made of lead, then electron will lose a lot of energy already, because LR, radiation length, gives you the length when energy decreased by factor 2.7. It's E, right? And if you have 1 centimeter, you already decrease the energy of electron. It will lose the energy by a factor of 3, 4 or so. Okay? So when you compute, if you want to have some kind of protection, you can keep this in mind. Now the question is, suppose we have lead and proton. What will be, this is for electron, what will be this for proton? And for proton it will be huge. If you remember this formula, the radiation length is inversely proportional to the mass of the particle. So that will be like a mass of the electron over mass of the proton square, roughly speaking, right? So something like this. And this is the radiation length for electron. Agree? And this is huge factor. So it's 1 over 4 10 to the 6 inverse, right? Radiation length. Because it's inverse, I have gotten this square, so that will be 4 over 6. So radiation length is proportional to the mass of the particle, right? Mass of the particle. Square. It's dE over dx is 1 over the mass of the particle. Squared, right? And radiation length is in the denominator, therefore radiation length is proportional to the mass of the square. And therefore, for proton in lead, the radiation length will be almost 7 orders of magnitude bigger than radiation length, bigger than radiation length in for electrons. And therefore, to protect yourself from the proton, it will easily penetrate, say, 1 centimeter, 2 centimeters, 10 centimeters. You need so huge amount of material to absorb protons, right? So it's easy to protect yourself from electrons, but more difficult to protect from protons. Although for protons, another energy loss will be more important, like ionization. So in the next I will discuss the ionization energy loss. No, 10 minuti.
Ok.
So, ionization. So this is the process when our particle, proton or electron, which enters the medium, knock out of atom one of the electrons. So we have a set of electrons, and this is our particle. And then one of the electrons is out of. The process, elementary process, is when we have L plus electron, we go to L plus electron. So now the energy of our particle is transferred partially to the energy of electron which goes out of atom. So, so diagrammatically this is again L, and now you can see diagrams of this type. Here is electron, scatter with gamma. Like in the previous case, let me write exact formula first, and then I will explain different factors which enter this formula. dE over dx, the energy loss, is given by 4 pi alpha square over mass of the electron. And then important factor is 1 over v squared. And this is the velocity of particle which entered the medium. So L is the velocity of this particle, squared. Then there is another factor, which I will not discuss in details, which depends on the mass of the electron, velocity of the particle L, and ionization potential. And multiplying by the number, density of electrons in the medium. So this is Bethe-Bloch formula. So let me denote again. So the VL is velocity. Which can be written as momentum of particle over the mass, VL. And therefore, dE over dx is proportional to the mass of the particle squared over momentum squared. Actually, opposite dependence from the previous case. Remember, in the case of radiation, the mass of the particle was in the denominator. Here is the denominator. So the heavier particle, the more it loses energy on ionization. So this is again mass of the electron. I'm sorry that we have kind of seen. What is here is mass of the electron. And this is related to the fact that we deal with atoms, essentially. This characteristics from that. Now we have alpha square. And alpha square here, because we have the process of the second order. Here we have 2 electronegative couplings, here, and And therefore, it's not alpha cubed, as it was in the previous case, but alpha squared. And again, I will not discuss this fact that it has a logarithmic dependence on energy of the particle. So it's proportional to logarithm of energy of the particle. This is a relativistic fact. This is a relativistic fact. And let me give briefly an interpretation of this dependence. So this is the most important factor, which you should remember, because that explains many features of experimental results, 1 over V. And it comes from the fact that ionization is proportional to time squared, which particle spends inside the atom. So you have atom, and particle moves, L, and if it moves slowly, then it has more chance to knock out an electron. And the chance decreases when it moves very fast. So it's time particle spans crosses the atom. So what is this time? Time is given the size of the atom over velocity. And this is the origin of 1 over V dependence. And this is final comment. Actually, again, one can derive this formula of major factors here from physical arguments. And this is because dE over dx is proportional to energy loss in each collision multiplied by sigma and multiplied by number density of the electron. So this is again the probability that particle interacts in the unit of volume, and this is the energy loss in each collision. Now, this energy is comparable with Rydberg energy. And Rydberg energy is alpha squared multiplied by mass of the electron over 2. This is essentially the energy of ionization of atom, which is energy which is required to ionize the atom. Now, cross-section is given by pi, Bohr radius, multiplied by opacity factor. So that is just R squared. This is the area. And this is the probability that even if you hit this area, the particle will interact. And this K equals alpha squared over V, velocity squared. Of course, it should be proportional to the coupling constant, and it is proportional to velocity. Now, RB, this is Bohr radius. Let me remind you that this is 1 over alpha ME. Now, if you put all these factors into this formula, then you will reproduce Beth and Bloch formula. So questions, that's it for today. So you see, if you even don't remember what kind of exact form, how it looks like, you can, to a large extent, reconstruct it. No need to, just using physical arguments, no need to remember many things. You can just reconstruct it because the most important is 1 over V dependence. And, or it is, so the energy loss is proportional to the mass square over momentum. Therefore, the bigger the mass of the particle, the more it loses the energy over ionization. And again, the smaller p momentum of the particle, it loses energy more. So slow particles lose the energy more. In contrast to the previous case, remember, I will summarize next lecture all these features, and then to a large extent have an opposite dependence. Radiation decreases when you have when the energy decreases, because energy loss is proportional to energy of the particle itself, and therefore particle loses the energy, energy decreases, and the energy loss decreases. Here is opposite. So particle decrease, the energy of the particle decrease on ionization, and ionization becomes stronger and stronger. These features people use to identify properties of the particles and evaluate the mass of the particle. Okay, so if there's no questions, then see you tomorrow.